and welcome to everybody online for this webinar on aircraft communication system design. So the agenda today, we'll start with a short introduction, and then we will explore Dassault Systems SIMULIA's solutions for communication system design, including antenna design, installed antenna performance analysis, co-site interference analysis, radar detection, and finally, we will discuss how electromagnetic simulation is integrated into the Dassault Systems SIMULIA 3D experience platform. There are many trends in aerospace industry today making communication system design more critical and challenging than ever. There's proliferation in the number of aircraft and denser airspace, evolving aircraft technology, a lot of smaller aircraft such as drones and air taxis being developed, trend towards highly autonomous flight, demands for faster communication speed and bandwidth, increase in the number of antennas and sensors installed on an aircraft, and increasing use of lightweight composite materials. So how can we ensure reliability of communication and safety? Where are the best places to locate the antennas? Will the aircraft structure affect the antenna performance? Will communication systems interfere with each other? Is space available to route cables to the antennas? And finally, will small aircraft be detected? Let's see how simulation can help address these questions. So when working on a large project such as aircraft design, it's important that designers can easily collaborate and stay in synchronization during the digital design process. Dassault Systems provides a platform called 3D Experience for this purpose. We'll talk about this more later. The Dassault Systems CATIA product is extensively used in the aerospace industry for developing CAD models and assemblies. CATIA is embedded in the 3D Experience platform. Dassault Systems has developed a CATIA model of an open rotor concept aircraft, and we will use this model to demonstrate communication system design. One of the key components of a communication system is the antennas, and it's important to evaluate how antennas perform when they are installed on the aircraft. However, antenna models are not always easily accessible, so this can be a roadblock for simulation. Fortunately, SIMULIA provides a powerful suite of tools for antenna design. So let's move on to this topic of antenna design and explore the possibilities. SIMULIA's Antenna Magus tool enables rapid generation of fully parameterized antenna models for simulation. The tool contains hundreds of antenna designs. So let's take a look at how it works. The starting point is to select a specification. So we select aeronautical airborne antennas, and we browse down looking for a GPS type of antenna, sorry, VHF. So Magus then presents the most suitable designs at the top of the list. And here we're going to pick a blade antenna, check information about the antenna, how it works and the typical performance. And then, once we've looked at the results that it could generate, we can switch to design mode. And we can check the parameters of the design, tweak them if necessary. And we can also then estimate the performance of the design. And it uses inbuilt solvers to calculate the response of the antenna. We can then look at the results, such as the reflection, S11, and also the far-field radiation pattern. So we can then export this design to 3D as a 3D model for electromagnetic simulation. We can give a name for the model. And then Antenna Magus launches the CST electromagnetic simulation tool, CST Studio Suite, and automatically creates the three-dimensional model, which is fully parameterized and ready to be simulated for fine-tuning of the antenna performance. For some communication systems, we may need antenna arrays, typically when a narrow beam is required, when we need higher gain, and also for beam forming, where the beam direction is electronically scanned. Design workflow usually starts with infinite array analysis. Uses a unit cell boundary condition approach to give the appearance of an infinite array. And this enables quick simulation to bring the design into specification. Following that, full array simulation is used to check the performance with a finite number of elements, for example, to check for edge effects. And both the infinite and the finite array models can be easily generated using the array tool in CST. Also want to mention that there is a video specifically about array design available from SIMULIA at the link on the top right-hand corner of the slide. But let's take a quick look at how the array tool works. So we start with the array element, and we create an array task in the CST schematic. We can then enter the shape of the array, circular in this case, and define the number of elements. You can choose which elements are active, passive, or absent. And you can also look at the excitation profile, which is initially uniform, but can be changed to be, for example, a Taylor distribution, as shown here. So we can then generate the unit cell simulation project, and the tool will automatically choose the frequency domain solver, which is the most relevant solver for that kind of analysis, and set up the model with the appropriate unit cell boundary conditions ready for simulation. We can also create the full array model. Again, it will choose the appropriate solver, the transient solver in this case, and generate the full 3D finite array model ready for analysis. In both cases, the models are parameterized so that we can easily steer the beam and investigate the performance for different scan angles. Let's look at some important results from the infinite array analysis. You can see the beam scanning on the left. As the beam scans to wide angles, the impedance becomes high, and this limits the operating range for beam scanning. The active element impedance is plotted on the right. The x-axis is theta in degrees, and the y-axis phi. The color represents the reflection level. Ideally, it would be blue or low. So scanning beyond 50 degrees, plus or minus 50 degrees, will result in poor performance, where the red spots are located in the picture. For the finite array, we may wish to investigate the impact of placing a radome cover over the antenna, and maybe the effect of another array located nearby. Radome in this case is made from a sandwich of epoxy, honeycomb epoxy layers. This is a satellite communication antenna. The large array is the uplink transmitting over the band 13.75 to 14.5 gigahertz. The smaller array is for the downlink receiving in the band 10.7 to 12.75 gigahertz. We can efficiently model radome using a thin panel material type, since the radome is electrically thin in the satellite communications frequency range. Its transient TLM solver offers ideal meshing for handling the detail around the elements of the array while minimizing the number of mesh cells in the space around the antenna. Here we can see an animation of the electric field distribution, which shows the influence of the radome. The change in dielectric constant from the air to the radome material causes reflection, and some of the field is trapped under the radome. The radome also changes the radiated beam profile, and there may also be some coupling from the uplink to the downlink array. So let's now explore SIMULIA solutions for analyzing the installed antenna performance. So we've collected some typical antenna types for placement on the open rotor aircraft. Let's take a look at these. So there are 3 VHF communications antennas, 2 on the top and 1 on the bottom. These are all blade antennas designed to operate in the 118 to 137 megahertz VHF band. They transmit and receive in various channels within this band. Radome covers were also designed for the antennas. We were previously discussing the satellite communications antenna, which includes 2 circular-shaped microstrip patch arrays. We will place the arrays with their radome on top of the aircraft to check the installed performance. As mentioned previously, the satellite communications array uses beamforming to point the beam in different directions. which is used to track satellites during flight and maintain a strong communications link. Next, we add a GPS, navigation antenna, receive antenna, which uses a 4-element microstrip circular patch array. The antenna is located on the top of the aircraft near the front. This antenna receives from satellites in the L1 frequency band at 1.575 gigahertz. At the front of the aircraft under the nose radome, we place a glide slope antenna, which receives at 332 megahertz. This antenna receives a signal from the airport that is used to guide the aircraft vertically to the runway when there is poor visibility. The glide slope is essentially a loop antenna. We also place a landing system localizer, or ILS, receive antenna operating at 113 megahertz. This antenna is used to guide the aircraft to the center line of the runway. We're using an inverted F antenna from antenna makers to model this antenna. The aircraft also has some detection antennas. One is the distance measuring equipment, or DME, which measures the slant range or distance between the aircraft and a ground station. We're using a monopole antenna with a conical shaped element for this DME. The antenna is tuned to operate effectively in the roughly 800 to 1200 megahertz range, covering the DME receive and transmit bands. Finally, we add a waveguide array, which represents the weather radar operating at 9.345 gigahertz. This array uses offset slots as the radiating elements. The antenna is mechanically steered to point the beam in different directions. Before we look at the simulation methods and results, let's see how the 3D experience platform is used to organize our design project. So the aircraft model and the antennas can be collected together into a collaboration space on the 3D experience platform. We can then select the aircraft model and open the CST connector, and this will bring the model into CST, maintaining a link with the 3D experience platform. We can then go and pick different antennas, such as the VHF antenna, and also, let's say, the GPS antenna, and bring those into the CST simulation project. Notice that there are anchor points on the aircraft, which are convenient for placing the antennas. And we can snap the anchor points to position the antennas on the airframe. So here's moving the VHF antenna into place. There are very easy to use rotation and twist features to put the antenna exactly in the right position. So this makes it very convenient to collect the antennas and place them on the aircraft for the install performance analysis. Finally, we can define a simulation task, in this case using a hybrid solver, which we'll talk about more in a minute. So that makes the whole workflow very, very easy to set up the model. And throughout this, CST is connected to the 3D experience platform so that any changes that are made are stored back to the collaboration space. Other teams can leverage the updates, digital continuity is maintained. All design teams can work from the same single source of truth model, and the CAD model updates are synchronized. The platform also enables teams to share results and to work on design of experiments and multidisciplinary optimization. Okay, let's now talk about how we go about simulating electromagnetic fields to obtain the installed performance. Key point here is that the antennas operate over a wide range of frequencies. The size of the aircraft in terms of wavelengths is important. We call this the electrical size. If the aircraft is, for example, 30 meters long, at 300 megahertz, it is 30 wavelengths, which we may say is electrically small to medium. At 3 gigahertz, it is 300 wavelengths, which is becoming electrically large. At 30 gigahertz, it is 3,000 wavelengths, which is, let's say, electrically huge. So for electrically small to medium size problems, the transient solver is a great choice. For example, for VHF install performance analysis. As the electrical size increases, hybrid solutions are the recommended approach. The transient solver in this case simulates the antenna detail. This is combined with another solver to handle the electrically large aircraft platform. For example, DME and GPS may be simulated using a hybrid transient integral equation method. And SATCOM may be simulated using a hybrid transient asymptotic method. So here we see some results for the VHF antenna install performance. And we're animating the electric field radiating from each of the 3 VHF antennas. There's 2 on the top and 1 on the bottom. Notice that there's coupling from one VHF antenna to another. And there's also some coupling in through the windows of the aircraft to the interior. If we analyze the far field radiation pattern of the installed antenna, we can compare the pattern for the antenna on an ideal ground plane versus installed on the open rotor aircraft. So for the ideal ground plane, the far field pattern is very smooth and it sort of resembles a donut. There's it's uniform in the azimuth and there's a null in the z-axis. When placed on the aircraft, the pattern is more complex. There's a lot of lobing and nulls which may affect the communications performance. When the antenna radiates, surface currents are induced on the metallic parts of the aircraft. The whole aircraft essentially becomes an antenna, and so the antenna pattern is changed. The level of impact on the pattern depends on several factors: the antenna type, the antenna position, and the wavelength. The VHF blade uses the aircraft as a ground plane, so the aircraft geometry has a strong influence. Here we can see the effect of sweeping the position of the VHF antenna, the one that's located on the top of the rear. So we're moving it over a range of 0 to 5 meters. And you see that the radiation pattern changes significantly with antenna location. The influence of different parts of the aircraft structure, such as the wings, for example, changes as the antenna is moved. There are some deep nulls at some locations in some directions, and it's hard to predict where the best locations could be, which is why analysis is so beneficial. It's perfect for performing a design of experiments to find the best optimal location. Location of the antenna not only affects its far field pattern, reflection into the antenna port, S11 or the VSWR, is also impacted. A plot of S11 is used to measure this performance. The KPI is to minimize S11 so that all the transmitter power is radiated. As the antenna is moved over a 5-meter range, the performance changes by 5 dB or so. The effective bandwidth of the antenna may be reduced because of this. Another important design consideration is the coupling between antennas. In this plot, we show coupling in dB versus frequency in megahertz. There are multiple curves, each representing a different location of the VHF top rear antenna. The solid curves are results for the coupling between the top rear antenna and top front antenna. The dotted curves are results for the coupling between the top rear antenna and the antenna underneath the fuselage. The requirement for isolation may be, for example, 35 dB. Coupling between the two antennas on the top exceeds this level. If we zoom into the VHF band from 118 to 137 megahertz, you'll notice that the worst case coupling is 5 or more dB over the threshold, but it depends on position. The solid red curve almost meets the requirement, but this is when the antennas are furthest apart. Installed performance of the glide slope antenna is shown in this slide. It's located under the radome near to the radar. As mentioned before, the glide slope is used for navigation during landing. The far field receive pattern at 332 megahertz squints upwards. Ideally, it would focus the energy downwards towards the distant runway. By plotting the electric field, we can see that the radar structure is blocking the GLS antenna. Using reciprocity, the antenna is transmitting in the simulation, but that's reciprocal to the antenna receiving. The presence of the radar causes the beam to point away from the ground. This kind of analysis can be used to check that sufficient signal is received, otherwise the range of operation may be limited. Let's look at the installed performance of the DME, distance measuring equipment antenna, which operates at 1.09 gigahertz. Again, we use for this a hybrid method using a unidirectional coupling between the transient TLM solver and the integral equation multi-level fast multipole method. In this case, the coupling between the solvers is unidirectional. It can be bidirectional, and we'll see an example later where that's important. So in this case, the detail of the antenna is simulated by the transient solver. The structure of the aircraft geometry is simulated by the integral equation solver. The DME frequency is much higher than VHF, so the aircraft is electrically larger. The far field pattern is less perturbed, looks more similar to a monopole, with some rippling due to the influence of the aircraft structure. Here we are plotting the surface current flow on the aircraft. You can see high current, red, the red color around the DME antenna. This current spreads over the airframe. The current on the underside of the wings has some influence on the radiation pattern. The wavelength is very small at this frequency, which is confirmed by the fine oscillations in the phase animation. In the hybrid solution, the integral equation solver only needs to mesh the surfaces of the aircraft, not the volume, which makes it efficient for electrically large structures. Next, we will consider the installed performance of the GPS antenna, which is a 4-element patch array. Again, we use a hybrid solution, combining the transient solver with the integral equation method. The transient solver, again, handles the detail of the antenna. In this case, it drives the 4 ports of the antenna with phase shifts to generate circular polarization, which is required for GPS. Despite the electrical size of the aircraft at 1.575 gigahertz, the full geometry is simulated efficiently. Next, we consider the installed performance of the weather radar operating at 9.345 gigahertz. In the CST Studio model, the bounding box is used to restrict analysis to the nose region, and then a bidirectional hybrid solution connecting the transient finite integration technique and TLM solvers is used to capture the interaction between the antenna and the radome. So in this case, the transient finite integration method is used to model the detail of the waveguide array, and the TLM method for the platform, which is the front part of the airframe and radome. The radome materials are modeled using a multi-layer thin panel model for efficiency. Finally, we consider the installed performance of the satellite communications array. For this, a hybrid transient asymptotic solution is used. Transient solver is used for the detail of the array, including its radome. The asymptotic solver is used for the platform, since the aircraft is electrically huge at the satellite communications frequency of around 14 gigahertz. We can run a parameter sweep to change the array scan angle and check for any directions where the aircraft geometry affects the main beam or side lobe levels. So we have seen how different methods can be combined to handle what would otherwise be very challenging simulations. Another key aspect of communication system design is co-site interference. So let's explore this topic more. SIMULIA provides a workflow specifically for this analysis and uses something called the interference task. This enables radio models to be defined and connected to the antenna ports. Radio models may include transmitters, receivers, components such as splitters, and we also use the S parameter block generated by the CST 3D electromagnetic simulation, which contains all of the information about coupling between the antennas. So let's perform co-site interference analysis for 3 antennas, the VHF, DME, and GPS, which are located near to each other at the front of the aircraft. So here we can see the spectrum of the VHF transmitter. It operates in the band 118 to 137 megahertz, and the power level in this band is 10 dB watts. And it has multiple channels within this band. But the transmitter creates harmonics of these channels, which extend to high frequencies. We're modeling this using a Duff model for the tapering, which brings the harmonics down to nearly minus 60 dB watts at 1,600 megahertz. So this electromagnetic noise may interfere with other communications systems. Here we see the sensitivity spectrum of the DME receiver. it receives in the range of -30 to almost -120 dB watts, which is a very tiny signal. And the sensitivity spectrum of the GPS receiver. And this receives in the range of just below -20 dB watts to almost -160 dB watts. Very, very small signal. It needs to be very sensitive as the signal from the satellite may be very weak. So we can overlay the VHF transmitter power spectrum with the DME receiver sensitivity spectrum. And here we see that the 7th harmonic band of the VHF overlaps with DME. If we do the same for the GPS, we see that the 12th harmonic band of the VHF transmitter overlaps with GPS. So in other words, if we plug the VHF radio into these receivers, we would have significant interference issue. But if there is sufficient isolation between the antennas, this may be avoided. So let's simulate and see. So for the coupling or isolation analysis, we need to either use a single solver to capture all the interactions or a bidirectional hybrid approach. Fine frequency resolution is important for this kind of co-side interference analysis to capture coupling for all the harmonics of the radios. So we may, for example, use the transient solver for the lower part of the spectrum, as it provides broadband response with very fine frequency resolution. And then we may combine this with a bidirectional hybrid transient integral equation solver for the upper part of the spectrum. Another option would be to use brute force simulation using the transient solver and high performance computing such as MPI. SIMULIA offers all of these different solution methods. So here's the schematic for the coupling analysis. The antenna coupling S parameters from the CST Studio simulation are available in the block, and several circuit components are added around this. For GPS, we're modeling some phase shifters using different lengths of transmission line, 90, 180, 270 degrees phase shifts. And then we use power combiners to collect the power of the GPS receiver. Overall, this creates a 3-port system. Port 1 is the DME, port 2 VHF, port 3 GPS. So results for this 3-port system over a broadband from 0 to 1600 megahertz are shown in slide. And you can see the operating bands of the antennas. VHF below 200 megahertz, the blue curve, DME around 1000 megahertz, the gray curve, and GPS at 1.575 gigahertz, the green curve. The orange curve shows the VHF to DME coupling, which is below -80 dB around the DME band shown by the circle marker in orange. The VHF antenna is on top of the aircraft and DME below, so this helps maintain good isolation between those two antennas. The red curve shows VHF to GPS coupling, which is around -70 dB in the GPS band, again shown by the circle marker in red. It seems like weak coupling, which is promising, but is this isolation level sufficient? For that, we need to run the interference task, which combines the coupling with the radio models, and it outputs a simple interference violation matrix. In this matrix, the rows are the receivers and the columns are the transmitters. And green indicates that there is no interference issue. Red highlights a potential problem. So in this case, when the VHF transmits and GPS receives, there is an interference violation. Isolation between the antennas is not sufficient, but they are only 2 meters or so apart in this case. The interference task provides more details about the interference violations. We can display the critical in-band interference margins for the GPS receiver. And this shows that 4 of the VHF channels are causing interference. Channel 14, 54, 102, and 159. Channel 159 is the worst case, that's the orange line, with a interference margin of 41.25 dB. So we could try increasing the distance between the antennas to around about 5 meters, but unfortunately the result is the same. There's still an interference issue indicated by the red square. So let's again check the interference margin. Well, the same channels are causing interference, and channel 159 is still the worst case, but separating the antennas has reduced the margin from 41.25 down to 34.57 dB. But it may be difficult to find an antenna location to provide an additional 35 dB or so of isolation, so we probably need a different approach. So what we can do is try adding a bandpass filter to the VHF radio output. And SIMULIA offers several filter design tools and workflows. One of these is the CST Filter Designer 3D. This enables rapid synthesis of a filter design to deliver a required filter response. You can simply enter the start and stop frequencies of the passband and the number of resonators, the type of filter resonator, which is a cavity type in this case, and then the tool will generate a 3D model ready for simulation. It also works in tandem with the CST solvers to rapidly and accurately optimize the filter response, which is a huge time saver. So results for the 3-port system are shown here with the filtering applied to the VHF radio output. You'll see that the VHF passband is more sharply defined. The unfiltered response is in blue, the filtered in red, and this is behaving as expected. The coupling from VHF to GPS is significantly reduced outside of the VHF band as desired. This is shown with the black curve, which is unfiltered, and the green, which is the filtered response. So we rerun the interference task using the filtered coupling results, and we now see that all the co-side interference issues have been resolved. So another topic that's important in aircraft communication design is the detectability of aircraft. With the increase in air traffic density, detection is ever more critical, and this is compounded by the trend towards higher levels of autonomous flight. Be further complicated by the proliferation of smaller aircraft such as drones and air taxis. So the radar cross-section of an aircraft is a measure of its detectability. The size, materials, and shape all influence the radar cross-sectional RCS. Composites, especially non-conducting, will tend to reduce the RCS. Monostatic radar cross-section considers the scattering back towards the radar source. We can run a parameter sweep to solve for the RCS for different angles of incidence, and then output a 3D plot of the profile. Here we see the profile for a small air taxi aircraft. The scattering is relatively small from the front and sides, much larger from above and below. They may be necessary to design in scatterers to ensure that the aircraft is sufficiently detectable. This will of course need to be harmonized with other requirements, for example, such as aerodynamics. Finally, we will revisit the topic of the 3D experience platform. As mentioned earlier, SIMULIA's CST electromagnetic simulation can be connected to the 3D experience platform. This ensures digital continuity of models during the design process, enabling seamless collaboration. Design of experiments can be run on the platform and results shared between teams to facilitate design reviews and make decisions. CST results such as coupling data and far field patterns can be displayed directly on the platform using the 3D Play application. So putting all this together, we've seen that our solutions for communication system design include tight integration between CAD, CATIA, and CST simulation to ensure digital continuity, rapid and easy antenna prototyping using Antenna Magus and the array tools, easy integration of antennas onto aircraft geometry using assembly modeling and anchoring, parameterization and powerful design of experiments for antenna placement analysis, tracking of antenna key performance indicators such as radiation pattern and power delivery, and an interference workflow which enables the antenna coupling to be combined with radio system models for co-side interference analysis. Before we wrap up, I just want to mention a related industry process. So aircraft must also be designed with lightning protection in mind. An interesting aspect is that antennas installed on the aircraft may actually attract lightning. The probability of the antenna being struck depends on the antenna shape, especially its conductive elements, and where it is located. Electrostatic analysis can be used to study this. Charge is applied to the aircraft and the electric field distribution calculated. The distribution is plotted in the slide for a VHF antenna installed on the open rotor aircraft. The red spots indicate high field intensity regions where lightning is most likely to attach. We can see in the results that the tips of the wings and tail and the nose are high probability regions. However, zooming into the antenna, we can see that the top edge of the blade is also susceptible. So this is another factor that can be considered during the placement optimization. Simulation is ideal to work through all the various scenarios in a virtual design or digital twin. Powerful visualization can really help designers make informed decisions. So here is an example of a movie showing various lightning strike scenarios for the open rotor aircraft. Here you can see the open rotor flying in a storm. As mentioned, certain locations on the aircraft may attract lightning. For example, lightning may attach to the nose and exit at the wingtip. A huge current will flow through the aircraft, and visualization of this current flow helps us to understand where the airframe may need better lightning protection. Different scenarios can be simulated. Here's a wing-to-wing scenario, or a tail-to-wing scenario. And these different scenarios can be simulated and even solved in parallel on a HPC cluster for efficiency. So to summarize the presentation today, Dassault Systems SIMULIA offers powerful industry process solutions for aircraft communication system design. The integration of electromagnetic simulation with 3D Experience platform enables tight collaboration between design teams. Hybrid electromagnetic solver technology delivers impressive scope and scalability. And all of this adds up to potential significant time cost savings benefits for the aerospace and defense industry. So thank you for attending the talk today. Back to you, Stephen, for any questions.